we talked about some mechanical vibrations that weren't forced. You could have a mass on a spring and you could possibly have a damper attached. Now we want to say, what if in addition you're pushing the mass with some force that depends only on time? That'll be force vibration. And then there's an analogy in the circuit model. You can drive the circuit with an additional voltage and you get the same kind of behavior. And there are other systems that do this too. But there's very interesting behaviors to this that are qualitatively useful in mechanics and other fields, just like there were with unforced vibration. Remember, in unforced vibration, you could have the mass on the spring could engage in simple harmonic motion up and down with a sinusoidal position as a function of time. If there was no damping, if there was damping, you had three different cases. You could have underdamped, you could have critically damped, or you could have overdamped vibration. Well, what happens if you also attach a driving force that happens to be sinusoidal? That's the interesting case for us. Well, we can get different kinds of behavior here also. Here's the model. We have first an undamped mass on a spring with a driving force attached. So md squared dt squared is mass times acceleration equals minus ku is the spring force you put over on the side, plus this additional force, which is actually expressible as a single sine wave. Remember, if you take two sine waves, sine or cosine, of the same angular frequency, they add to a single sine wave of that same frequency. So this is the mass times acceleration equals the spring force minus ku plus this force. And we'll put the ku plus ku over on the left instead of minus ku on the right, just for convenience here, because now, how do we solve this thing? Remember, this is a non-homogeneous, linear, second-order differential equation with constant coefficients. So you first put 0 on the right and solve the associated homogeneous problem, sometimes called the complementary problem, I think, in your text. And then we find a particular solution with this right-hand side in here, just any one solution whatsoever, and when we add the two of them together, it gets us the general solution of this non-homogeneous problem. So we first look at the homogeneous problem. Left side, md squared dt squared plus ku equals 0 on the right. And we recall that homogeneous problem had as its general solution c1 cosine omega t plus c2 sine omega t, where omega was square root k over m. That comes from the characteristic equation. If you divide through by m, it becomes d squared dt squared plus k over mu equals 0 on the right. And when you solve the characteristic equation, it has solutions plus or minus square root k over mi, and so if you had just 0 on the right, you got this general solution. Now what happens with this on the right? If you look at that method of undetermined coefficients that we spent so much time on before, we found that the form of a particular solution was this one. And so we could plug this into the differential equation and find out what the constants, the unknown constants, gamma 0 and delta 0 were. And then we'd have the general solution was to the non-homogeneous problem, this one here, force vibration, was the homogeneous general solution, c1 cosine plus c2 sine, plus this particular solution here. And these two here are arbitrary constants, right? In the homogeneous problem, you let c1 and c2 be anything and you get a solution. But these two are not arbitrary. These, what you do is you plug this into the solution, into the differential equation, and there's specific constants, gamma 0 and delta 0, that satisfy the differential equation. And so you take this with c1 and c2 arbitrary and add it to this with gamma 0 and delta 0 determined by plugging in, and this gives you the set of all solutions of the non-homogeneous problem. Well, if you think about it, what we did before, here's a sum of two sine waves with the same angular frequency at omega equals square root k over m coming out of the left side. they can be combined to a single sine wave. Some sine, A sine omega t plus b. Remember, A is square root of c1 squared plus c2 squared is the amplitude of this wave when you add these. And omega can be, omega is square root of k over m is already determined, and phi can be determined with an arctangent, possibly plus pi. Depends what quadrant you're in. So these two can be combined just by trigonometry to make a single sine wave. Similarly, these two have the same angular frequency. Whatever the angular frequency your driving force is. The idea is you're driving this with a sinusoidal input of angular frequency omega 0. And that forces the vibration of the system at the same angular frequency. Is what the undetermined coefficient table tells you. So you have a solution of this form, and these two, since they have the same angular frequency, are also expressible as the same, a single sine wave, whose amplitude, say A0, is root sum square of these two numbers, gamma 0 and delta square 0. And then it drives at the same angular frequency, and psi 0 is also computed by arctangent with this one using trigonometry. So actually, if you think about what the motion is, all you're doing is you're using the math you've already done to solve an equation of this form. That's all I'm saying. When you do, you get a solution of this form that can be written actually by trigonometry as sum of two sine waves. And so what does the motion look like? That's what's of interest here. Got a picture down here. You have a sine wave that's this red curve. That might be your homogeneous solution, C1 cosine omega t plus C2 sine omega t. And then you have a particular solution, that's this curve. That comes out of driving this with some sinusoidal push back and forth in time. And so the oscillator wants to oscillate at this natural frequency that it would do if you just pulled it and let it go. But you're pushing it also at this other, with this sine wave of another frequency. And the result is a solution that's the sum of these two. And when you take this one and stack it on top of the red one, right, the magenta on top of the red, you get this kind of purplish one. That's the sum of two sine waves. And so it repeats over and over like that. That's the motion when you drive a mass on a spring with an additional driving force that's just a function of time at some other frequency, not the frequency of that it naturally wants to go at. Well, what would happen if I drove it at the same frequency as it naturally wants to oscillate at? An interesting thing happens. You can kind of imagine, really. If it's oscillating like this anyway, every time it comes down, I push it a little harder, and I push it a little harder, push a little more, push a little more each time. Then it starts with, there's no damping in here, right? There's no damper, it's just the mass, the spring, and we're assuming no friction. If you just push a little bit more each time, it starts getting bigger and bigger oscillations, and that is called resonance. And here's what happens in that case. Find it somewhere. There we go. Let's look at this case here. If omega equals omega 0, so the natural frequency it wants to oscillate at, square root k over m, is equal to omega 0, the frequency I'm driving it at, then you apply your methods from before. It's no new methods to solve differential equations. The particular solution has to have this t in it, because the table of undetermined coefficients says you should drive it at this rate. If it's not a solution to the homogeneous problem, but it is, right? If omega equals omega 0, then the particular solution has the same angular frequency as the homogeneous terms, and so you have to multiply by t to get a particular solution. Well, if it looks like this, what is this? This again is a single sine wave, but multiplied by t, it gets a growing sinusoidal. It's a growing oscillating function, and it looks like this. You start out just with your sinusoidal oscillation of the oscillator, but now you're pushing it, pushing it, pushing it, and it builds up bigger and bigger oscillations. Here's the T motion, right? You're taking a sine wave times T is what you're doing to create that. And then on top of that, there's an additional sine wave that's just going like this. It's hard to see down here because it starts getting overwhelmed by what is actually the particular solution. So the point is, when you drive a mass on a spring with a force that has the same frequency as the oscillator naturally wants to move at, the motion is a sine wave plus t times a sine wave, both at the same frequency. And this one just remains oscillating steady, but this one builds up bigger and bigger amplitudes. The particular solution grows larger and larger and eventually overwhelms this one, and you see that motion we saw at the end. So this is a nice qualitative understanding of the things we already derived from our differential equations. What does it apply to real life situations? It says that if you take your sister in the swing and push her, and she goes a little higher, and every time she comes back, you push her in the same position. If there was no friction in the spring, in the swing, she'd eventually go over the top, right? This is, it's a good thing the swing has friction, right? What you're doing when you push it each time the same thing is making up for the loss of friction. If that weren't there, you push her up over the top. Now, there's one more thing we can consider. What happens if we drive it real close to the same frequency at which the oscillator naturally wants to go at, right? This mass on the spring wants to go with simple harmonic motion. And if we push it right at that same frequency, it gets bigger and bigger and bigger oscillations till the spring breaks or something. And if we push it at an off frequency like we showed, well, it's just kind of the sum of two sine waves and it moves a little jerky, but you can see the two individual motions and it doesn't build up. What happens if we push it close to the same frequency but not exact? Well, you'd think maybe something kind of in between would happen, and sure enough it does. If you push with omega 0, your driving angular frequency, not equal to the angular frequency square root k over m that the thing wants to oscillate, but real close, then when you apply this trigonometry identity, that sine alpha plus sine beta is 2 sine alpha plus beta over 2 cosine alpha minus beta over 2, to rewrite the general solution that you got for the sum of two sine waves, you can rewrite it in this form. And so the first solution we did, driving at two different frequencies, can also be written in this form, but it's not very significant. It's just a clumsier way of writing the same thing you had before. However, if the two frequencies are approximately equal, almost equal, it's really useful to put it in this form because and I should say, part of it combines. This says if you take two sine waves with the same amplitude at different frequencies, you rewrite them like that. So what you have to do is take the homogeneous part of the solution and the particular part of the solution, take the smaller of their two amplitudes and add those together, and use trigonometry to combine those two same amplitude sine waves into a product of sine times cosine, using this trig identity for sum of trig functions. Can be rewritten as a product formula. It's called the sum to product formula. And then there's a little bit of amplitude left over, right? Whatever the difference in the amplitude was multiplies the remaining sine wave. So we have a sum of two sine waves plus a constant sine wave. And now this one, however, is very interesting when the frequencies are very close to equal. Because now this says you have, this is very, very close to 0, but not 0. So it's a very small frequency. And you have long waves, right? The wavelength is inversely related to the frequency. So this has a real long wavelength because it's got a low frequency. This one, however, when you add them, is much higher, and so you have a high frequency sine wave times a low frequency sine wave, and you get what's called the phenomenon of beats. And I've got a picture here. Here it is. It looks like this. And what you get this very interesting result where your solution is actually the sum of two sine waves that are going at a constant frequency, right? Just like the picture I showed you before, right? If we have sine waves of different frequencies, you can get this constant motion like this. But when the frequencies are real close to each other, these things start to add up to look like this, and now something significant happens. Even though each of the two individual sine waves going in have a constant amplitude, the resultant wave goes up and down and up and down and up and down, and you get the phenomenon of beats. You get this high frequency tone, but it goes up and down in amplitude. It goes there's a very nice video put out by MIT online I want to recommend to you where you can hear this. They strike a tuning fork, and you can hear it at one tone, and then take a tuning fork with a very close but different frequency, and they strike it, and the result is a sound that oscillates on and off, and you can say, how can that happen? Each tuning fork is making a constant sound. How can the sound be going on and off? Well, it's the phenomenon of beats. So that's what you can predict using trigonometry formulas together with your differential equations. All right, and the other thing is, how does this look like it's sort of a transition from the sum of two sine waves here, right, where it's just kind of a funny looking wave that goes over and over. How is it transitioning to this, the resonance case, right? When you're getting real close to resonance, this is what happens. And what happens is you start out as though it's resonance. You're getting larger and larger and larger and larger waves, and then, however, things start to damp back down, and then they ramp back up and they ramp back down. And so what happens is, as you get closer and closer to resonance, as you get longer beats, longer and longer beats, and eventually the beat goes to infinity and you get resonance. So that's how it transitions from the sum of two sine waves in undamped forced vibration to resonance. As it goes from sum of sine waves to this to an ever-expanding oscillation. All right, and all it is just applying the solutions you already know how to do to see this motion. All you did was take the solution you already wrote down and apply trigonometry. So that's the idea, is this is a trigonometry lesson. You take the things you already did and you use trig things to say, hey, look at this neat behavior that we got. So one of those three behaviors happens when you have undamped forced vibration. Now the question is, what if you also have damping? What if you have some sort of friction, or you have something else that slows it down? Suppose actually the damping is proportional to velocity like we did before. Now the equation changes to this. We've got md squared u dt squared equals, if I put this over here, minus ku is the spring force, minus c du dt is the dashpot damper we attached, and then we've also got this driving force. We'll put this on this side so we can look at a homogeneous problem and a non-homogeneous problem, but written as a force equation, that's what it is. The force, mass times acceleration, is equal to the sum of three forces, the spring force minus ku over here, the dashpot damper minus c du dt, and the driving force, a function of time only, which the interesting case is sinusoidal oscillations. And by the way, this applies to circuits very nicely because you have often an oscillating voltage when you're trying to drive an alternating current through a circuit. And so this is precisely the kind of thing you get in electronics engineering. Well, in this case, now that you have damping again, we first solve the homogeneous problem by putting 0 over here, right? And we get something that looks like this. It's one of three cases, remember, right? ignore these things on the right, we can get overdamping, C1 e to the R1t plus C2 e to the R2t, where R1 and R2 are both negative, because the MC and K were all positive, it'll force these to be negative. Or we can get R1 equals R2 negative, and we'll get this one, C1 e to the R1t plus C2t e to the R1t. Or we can get complex conjugate solutions and get this underdamped motion. So it's the overdamped, critically damped, and underdamped motions is the solution of the homogeneous problem when you didn't have the driving force. Now the driving force says that you have to add a particular solution. It's homogeneous solution plus particular solution. And the particular solution no longer can have can be a solution of the homogeneous problem, so you don't have to multiply by t like we did in resonance. It's just a sine wave added, a sine wave, a sine wave, a sine wave. We look up on the table of undetermined coefficients, and it's always a gamma 0 cosine omega 0 t plus delta 0 sine omega 0 t, regardless of the three cases. Well, what does that tell us about the nature of solutions? Here's the interesting thing. You plug in initial conditions to find these constants here, by the way. But the homogeneous part is decaying, right? All three of these homogeneous solutions that we did before were decaying. You could have overdamped, underdamped, or critically damped. And then you add to that a steady sinusoidal motion, right? This can be written as a single sine wave, and this, and this. It's all just the same thing added. And so we call this part that damps out the homogeneous solution the transient term, because it goes away. And we call this part that keeps beating away the steady state term. And so the homogeneous part is the transient term, and the particular solution gives you the steady state term. Here's an example. Let's do a circuit this time, because they have the same kind of equation. We drive it with maybe a 40 volt oscillating voltage. And here's the usual left-hand side of an LRC circuit, right? So we attach a voltage to an LRC circuit. And so we've got L is 1 times d squared q dt squared plus R is 4 times dq dt plus 1 over c is 13 times q equals the impressed voltage. Now Kirchhoff's law says the sum of the voltage drops across these three components is not equal to 0 anymore. It's equal to the impressed voltage, 40 sine t. And then there's an initial charge in the capacitor of 0 and an initial current, Q dot of 0, of 2 amps. So we're starting off with 2 amps and no charge in the capacitor, and driving this thing with 40 volts alternating sinusoidally. And what happens? We just go back to our previous sections that we said. First we solve the homogeneous problem by putting 0 over here. It's r squared plus 4r plus 13 equals 0. And we got r1 and r2 is r minus 2 plus or minus 3i. Oh, it's the underdamped case. And the homogeneous part of the solution is e to the minus 2t plus c1, or times c1 cosine 3t plus c2 sine 3t. Right? That's the general form of the solution for the undriven problem. But now we need to add a particular solution due to the fact that it's actually driven this time. If you plug in a particular solution, A sine t plus B cosine t, which is what, remember the table of undetermined coefficients, if you have a number times sine or a number times cosine, either one, you generally need both terms over here. You need a constant times sine plus a constant times cosine for a particular solution. If you plug that in and determine the coefficients, it comes out to be 3 sine t minus cosine t as a particular solution. And so you have this as the general solution. E to the minus 2t c1 cosine 3t plus c2 sine 3t. That's the general solution of the homogeneous problem, plus this particular solution, one solution of the problem that we found from the undetermined coefficients method. This is all solutions to the circuit problem. Now we apply the initial conditions. Q of 0 equals 0. If you plug that in, 0 on the left for Q and 0 on the right for T, it tells you that 0 equals, let's see, e to the 0 is 1 times C1 times 1. So it's 1 times C1 plus sine of 0 is 0. So you just get C1 equals 0. Let's see. I'm sorry, C1 equals 1, right? 1 times C1 equals oh, I'm sorry, C1 minus 1. I forgot this one over here. 0 equals C1 times 1 plus 0 minus 1. So you get C1 minus 1 equals 0. And then the second thing, if you take the derivative of this and set if the derivative when t equals 0 equal to 2, that similarly gives you an equation like this. I won't work through all the details. Tells you that C2 has to be minus a third by plugging in that initial condition. It's a bunch of derivatives. And you get that the charge in the capacitor anytime Q of t is equal to e to the minus 2t times cosine 3t times 1. Let's see. Maybe it should be minus a third. I suppose sine 3t. So C2 is minus a third. Plus the particular solution 3 sine t minus cosine t. So there's what you come up with. This might be minus a third, I think. All right, now what you do is you look at that and say, this is a sine wave, right? Same frequency set to a single sine function, times a decaying exponential. This is the transient term. This one is a single sine wave. We could again use the formula from trigonometry for that and write that as a single sine wave. We call this the steady state term. Well, there it is. So the same thing happens to a mass on a spring. Suppose I have this damp-driven mass, so the mass is 1, the damping coefficient is 2, and the spring constant is 5, and you drive it with the sinusoidal driving force minus 8 cosine 5t minus 4 sine 5t. Well, there's a particular solution. The homogeneous problem has characteristic equation r squared plus 2r plus 5 equals 0. And gives you r equals minus 1 plus or minus 2i. Oh, it's the underdamped case again. And now we also can plug in, and so we get this general solution of the homogeneous problem. E to the minus 1t cosine 2t and e to the minus 1t sine 2t are independent solutions. We write this general solution for the problem that has 0 on the right. Undetermined coefficient says there's a solution when you have a cosine plus b sine of the same form, a cosine plus b sine. And so we plug this into the differential equation. We find out that gamma 0 is 2/5 and delta 0 is 0. So it must be actually the particular solution is 2/5 cosine 5t. Once in a while you get lucky and one of these falls out, you don't need both terms. So there's a general solution. The homogeneous general solution plus this particular solution is the solution for the motion. Now if we also start with initial position 1 unit down and initial velocity minus 1, so the velocity opposes the direction of position, it turns out you just plug it in and you find out that C1 is 3/5 and C2 is 3/10. And here's your specific solution, 3/5 e to the minus t cosine 2t minus 1/5 e to the minus t sine 2t, underdamped. Plus, we have the steady state term 2/5 cosine 5t, and here is what it looks like. This is the homogeneous term, the transient term. This is the steady state term. And when you add them together, the red one's making a smaller and smaller contribution. There's this curve, eventually just looks pretty much like the steady state solution. So that's what happens in damped driven oscillators. You always get a transient term from the homogeneous part and a steady state term from a particular solution, they add together and it always settles down to the steady state solution at the end. The only difference is you might be adding a steady state term to an underdamped motion like this one, or it might be to a critically damped motion or an overdamped motion. In any case, it all just damps out. Here's a very fun example. You really should go click on this. This is a very fun video that I always show, and I'm sorry you have to miss it here. But you can click on this at home. It's on the notes. You can just click on it. I think control click on the notes and then you go there. At least paste this in your browser. This is the Tacoma Narrow Bridge in Washington, the state of Washington. And it's collapsing because in a measly 40-mile-an-hour wind like we get all the time here, the bridge fell down. It was practically new. How did that happen? Well, the engineers didn't realize when they built this new bridge that the wind blowing across it would cause it to oscillate with a vibration that was a resonant frequency of the bridge. And so the bridge started building up bigger and bigger oscillations in relatively common winds, and it built up huge vibrations. You have to see it to believe it, that this had actually happened in a bridge. And eventually fell down under these, the stress of wobbling up and down. So that's the Tacoma Narrows Bridge, an application. I should mention on here that technically this isn't undamped vibration. When you have bridges, there is actually a corresponding thing that we didn't mention about this. There is a frequency at which you can drive a damped oscillator. It's a little different frequency from an undamped oscillator, but from which you get a maximum response, where you put in a little and get out a lot, and that's what happened here. There is actually some damping here, and so you have to drive it at the resonant frequency of the damped system, which we won't discuss. It's a little more complicated, but it's essentially the same thing. And then here's a summary of all the different motions. If this is T, and this is the position up and down of the mass of the spring, you get this kind of motion if you just have a mass and a spring and that's it. If you add damping but not driving, there's three cases. You can get underdamped motion, critically damped motion, or overdamped motion. These all look pretty similar. This one oscillates though, and this one goes down the fastest since it's critically damped. It goes down faster than this one, or this one. If you have an undamped driven oscillator, then it's the sum of sine waves like this. If you happen, unless you happen to drive it near its characteristic frequency at which the thing wants to oscillate without the driving force, if you drive it at that frequency, you get resonance, bigger and bigger oscillations. If you drive it close to there, but not quite, you'll get a little sine wave left over, plus the beats like this. You should see this MIT video too, actually, by the way. This is quite good. And then finally, if you take a damped driven oscillator, you get a transient term that damps out and eventually steady state vibration. Those are all the cases that you can get.